What is entropy? If I ask this question, what is the answer off the top of your head? Maybe a lot of people will have this formula in their mind, but to be honest, I'm really not a big fan of this fancy sigma sum notation because it's not that intuitive. If I ask you to use non-technical language to describe entropy, what will be the answer then? Well, I would say it's the expected value of surprise. Just imagine a universe making up of three my favorite animal. So all the animals living there, um, it has three possibility. Either they are sea otter, or they are ice bear, or they are baby shark. Then we know that in this universe, the probability that an animal is otter plus the probability of an animal is bear and the probability of an animal is shark will equal to 1, right? And if there's a lot of otter, the majority is otter, then it will be the probability of seeing otter will be very high. And so that if we randomly pick an animal from this universe, we will we will not be surprised at all if we see the animal turn out to be an otter, right? So here, so we just use this fraction to describe how surprised we are when we observe an occurrence of some class. And we know that the logarithm of 1 on top of p can be written as minus logarithm p. They are the same thing mathematically. Thus, we'll see if we use p to describe the probability that we observe the appearance of an animal. If the probability is big, then this fraction, the value will be small. And if we calculate the logarithm of 1 on top of p, the value also decrease as p increase. So if we describe a surprise function, surprise for a class C as the logarithm of the probability of an observing an occurrence of C, then we know that as the probability goes up, the surprise will goes down. So let x to be a random variable, and it's belong to the set otter, bear, and shark. Then the expected value of surprise it's given by, right? It's just simple expectation calculation. But remember, our surprise function is described as logarithm 1 on top of p, and it's equals to minus logarithm p. So another fancy way to write the expected value of surprise is summing up. It's the same as the total entropy. And how does the total entropy score related to the class distribution? We can do a small experiment here. Say we have three type of distribution here, right? Say we have three planets. The first one, we can see on this planet there is 100% otter and no beer, no shark. And we calculate the entropy. So the entropy is 1 times minus log plus 0 times minus log and now we calculate the second universe. half of the population are otter, half of the population are bear, and no shark, then the total entropy is. Now the third universe, um, we have all these three type of animal: otter, bear, and shark, and the population are all the same. So the probability of observing the animal to be an otter or a bear or a shark is equal. They all equals to be 1/3, and the entropy will be. And now have a look at this, the entropy score of these three planets. We'll see the first planet, only one species, all otter, we call it otterverse, and the entropy is 0. And the second universe, we have otter and bear there, and no shark. The entropy score is 1. And the third planet, otter, bear, and shark, they all mix together. And the entropy score is the highest. It's 1.58 something. So the intuition here is, when the data set is pure, you only have a class, one class or two class, or there is a class that is highly dominate. Then the entropy score tend to be low. And when the data set is highly mixed, or all different class there mixed together, and the entropy score will be high. Now, with the above knowledge in mind, let's have a look at the cross-entropy formula. You'll find out it's quite similar to the formula to calculate the total entropy. The only difference is that instead of sub in the true probability, we sub in the predictive probability here. You will find out this formula is heavily used as a loss function when we are performing classification task. And how does this cross entropy score to do with our prediction accuracy? We can also do some experiment to find out. Let's say we have three class ABC, and we know the true distribution is that the probability of scene A is zero point 0.4, and scene B is zero point 0.3, and scene C is also zero point 0.3. So when calculating the whole data set's entropy, it's given by. And if we somehow we use some model to learn, we predict the probability that the data is in class A is zero point 0.5, and the data is in class B is zero point 0.2, and the data is in class C is zero point 0.3, then the cross entropy will be given by. We'll see. Currently our prediction is not quite the same as the true distribution, and the cross entropy score is also a bit higher than the true entropy. Just make a guess. Does the cross entropy have a global minimum? The answer is yes. It will achieve its global minimum when the guess is exactly same as the true distribution. And if you are interested, you can refer to Gibbs inequality. I will attach the link of the Wikipedia in the description section. You can have a read. So, cross entropy is a continuous differentiable measure of prediction error. The closer the prediction is to the true distribution, the smaller the loss is, and the better the model is. The concept introduced in this video is heavily inspired by Dr. George Stammer, the host of channel StackQuest with George Stammer. If you find my video helpful, like and subscribe. Until next time, keep learning.